if we were to draw another line, so we're, just for the video purposes, this is 1.3 continue, talking about theorems, and this is the theorem on the top of page 17. If you were to take, another line, and let's say we said, well, it's easy to see that any two lines are on the same plane. Here we draw any two intersecting lines, they intersect there at one point, they're on this plane right here. Okay, well that's easy to see, but what happens if I took a line here and I intersected it with a line like this? We'll call this a line, right? And it's intersecting. Well, are those on the same plane? And the answer is, well, they should be, because that's a theorem, which is true. But we have to visually see, we're not looking at just this whiteboard plane. Now we'd be looking at a plane that would be, a flat plane coming all the way and intersecting at that line at that angle. So even if you tip this like this, it would be a flat surface coming and intersecting with this line right there. So there's no way to draw two lines that aren't on the same plane. The plane just has to be, we have to visually see it in space. So with that, okay, on that theorem, I was going to explain to you, right? What does it say? T 1.3.2, yes, right? And so you have this dot, 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 talking about two lines intersecting, they're on the same plane, and then you see this, whatever, I don't know if your T is outside the parentheses, it's on the inside, doesn't matter. All this is referring to is, and it's specific to this book, because a different book would have it in a different spot, it's saying chapter 1, section 3, the second theorem in this section. So if you look at the first theorem they gave you, that was back on page 16. Do you see there it says T 1.3.1? And then the next one was T 1.3.2 on page 17. And then what's the last one? Two parallel lines contained in exactly one plane. What does that say? T 1.3.3. So if this was in section 1.4, it would say what? T 1.4, right? And so that's all it's referring to, and it's a way for you to reference in your book, oh, where was this theorem? And you say, oh yeah, it was in 1.3, and it was the second theorem given to me. If you have a different book from a different publisher, they may include this in 2.7, and they'd say 2.7.2, or maybe it was the seventh proof given, 2.7.7. Okay, so don't get hung up on that. That's just a way to identify where the proof is in this book. Okay, let's go to page 17. I actually don't want to write a lot of stuff down, so let's go right to page 17. You're there, and we are looking at number 1 there. Okay, so on number 1, we should all be there on number 1. It says, match each description with the proper characteristic of an ideal postulate system. So if you're following along in the video, you're going to have your book out and looking at page 17. So let's look at this. It says postulates do not contradict one another. Postulates do not contradict one another. Okay, so this isn't a true or false. This is a statement of you match it to A, B, or C. Postulates do not contradict each other. Is that independent, consistent, or complete? Now, if you're like, I don't know what those words are referring to, we can go back, right? And we can go back to page 15. So quickly go back to page 15, okay? And this is where we have our reference of independent, the word independent, and then the word complete, right? And then we can see over there back on page 14 is the word consistent. So let's actually go back to page 14. A postulate system is consistent if its postulates do not contradict one another. If two postulates of a system have opposite meanings, the system would be inconsistent and therefore defective. Okay, so consistent means if its postulates do not contradict one another. Okay, independent on page 15 says if no postulate can be deduced or proved from the other postulates in the system. And then 15, a system of geometric postulates is complete if it sufficiently describes the basis of the geometry. So a little, kind of a lot going on there, but let's see if we can get some of these. Go back to number 1 then. Postulates do not contradict one another. So if they don't contradict one another, they would be consistent. Okay, so B, consistent. Postulates do not contradict one another. They are consistent. Okay, number 2, the system forms a sufficient base for a full description. The system forms a sufficient base for a full description. What would number 2 be? If it forms a sufficient base for a full description. And if you're wondering, right, you can go back and look at, is it consistent, is it independent, or is it complete? What would that be? Possibly complete, yeah, because it forms what? A sufficient base for a full description. So if you go back to the definition of complete, it sufficiently describes the basis of the geometry. Okay, number 3, no postulate can be deduced or proved from the other postulates. No postulate can be deduced or proved from the other postulates. What is number 3? Independent. A is what we want there, independent. Good. Do postulates have to be proved? Now this is a yes or a no. Do postulates have to be proved on number 4? Yes or no? A postulate. No, postulates don't have to be proved. What has to be proved? Theorems. Okay? Theorems have to be proved. Now, name 3 things that can be used to prove a theorem. Okay, now where would we possibly find that? Because there's a lot of definitions and foundations. You could find it in the book, you could go back and look, but anybody know the 3 things can be used to prove a theorem? Anybody have one of them? Yeah, Abby.
It was right here. A definition.
Definitions, okay, good. So definitions can be used to prove a theorem. What else? What else can be used to prove a theorem? We have definitions.
Informal.
What?
Informal.
What are we looking at? Oh, those are types of proofs. Oh, good. Yeah, informal proof. Good job, Sean. That's a type of proof, but not used to prove a theorem. What do we have? Definitions and, yeah, even
Postulates.
Postulates, very good. And then previously proved theorems. And we're getting that reading directly from the book, right? So you can find that. So those are the 3 things that can be used to prove a theorem. Definitions, postulates, previously proved theorems. Okay. Fill in each blank with planes, lines, points, or space to complete each sentence. 3 non-collinear what lie in exactly one plane? What would that be? 3 non-collinear points on number 6. Yes, number 6 is points. All right, then number 7. 2 what are either parallel or intersect in a line? 2 planes. They're either parallel or they intersect in a line. That's what planes do, yes. All right, number 8. An infinite number of lines can intersect in one point. Yeah, infinite amount of lines will intersect in one point for number 8. Number 9. 4 non-coplanar points determine, space. Yeah. Because space is made up of more than just one plane. It's made up of multiple planes, right? So if it's 4 non-coplanar points, it means we've created space. It determines space. Number 10, if a line lies in a plane, then there are at least 2 what that also lie in that plane. 2 points that also lie in that plane. Okay, number 11 here, we're not going to go through all of these. I'm going to kind of transition, but just to make sure we understand, on number 11 here, it says, use the figure to answer each question, state the definition, postulate, or theorem that supports your answer. So for number 11, it says, does line AB lie in plane M?
Yes.
Okay, so visually we see yes, but why is that true? We can't just say, yes, it looks like it. We need to use a, what does it say? Postulate or a definition or a theorem. So Nessie?
Oh, I was gonna say because they're both points are on plane and you can always draw a line between 2 points.
Okay. What postulate might that be? You've given a good definition, Cash?
The flat plane postulate?
Yeah, flat plane postulate. So by formal definition, Nessie, you would say flat plane postulate, even though you're giving like a definition for it. So nice. Okay, so that's what you'll do on 11 through 17. Then we're going to go make sure that we're savvy on our next set of stuff. I guess on like numbers, if you go over to the next page, page 18, you can see 20 through 26, even though I think you're just doing the odds. Those are always, sometimes, or never true. Okay, so those ones, you'll continue to work through some of the stuff that we've already talked about. 3 points are non-collinear, things like that we've kind of discussed. And then 27 through 37 is some more of the name the postulate that verifies each statement. And then with 6 rectangular, use the box-like figure on numbers 31 through 36 to come up with some answers there for true or false stuff. Now, let me encourage you here with this type of material. If you look at what numbers that I assigned for you on 1.3, what's the first bulk of numbers? 1 through 39 odd. The temptation is quickly look at it, write something down, check the answer, get it wrong, erase, fill in the correct answer, right? The reason why I give you odds a lot of the times is so that you can grow in your learning, right? I'm not trying to hide information from you, right? So make sure, take a look at the problem, think through it, make your educated guess or your answer, and then go check the answer. If your answer's wrong, figure out why you're wrong. Check with your neighbor, check with me and say, hey, I put always true. The book said sometimes. That means there should be a false way to do it. Help me understand this. Does that make sense? So the learning gets put on you a little bit that you have to say, I want to understand why I got it wrong. I assign 1 through 39 odd to make your life not easy, but to help you succeed, right? You know the answers. That's awesome. Make sure you understand them. Make sense? And with a lot of this, it's not as simple note-taking. As you can see, we don't have like a lot of notes. It's a lot of definitions, and I don't want to be doing tons and tons of writing. So it's a little bit like we got to piece it together where we're doing some of the, looking at the book and looking at the definitions they've given you. So, okay, we're going to stop there. We're not going to go into 1.4. Okay, our plan is on Monday. We'll quickly grade 1.3. So when's 1.3 due? Monday. Okay, our plan is on Monday. We'll quickly grade 1.3, go right into 1.4, and try to finish 1.4 on Monday and have that be due Tuesday. We'll take it step by step, but that's the plan. You have the remainder of the time, which is a little bit of time, to work on 1.3. Any questions? If you're done with 1.3, help those around you that aren't done, or look ahead to 1.4. No problem with that. Just don't be disruptive. Yes?